we have the Henderson-Hasselbalch equation relating the pH of this buffer to the acid dissociation constant. And for the case where the concentration of the acid is equal to the concentration of the conjugate base, increasing these at the same time would not affect this expression, because log 1 is always 0. And therefore, the pH stays constant, but the capacity of the buffer is increased because you have more acid and its conjugate base to neutralize any added acid or base. Now, if the buffer has more conjugate acid than base, then it has a greater capacity for neutralizing an added base than an added acid. So effectively the hydroxides are neutralized by the acid. And conversely, when the buffer has more conjugate base than acid, then the buffer capacity is higher for neutralizing an added acid rather than a base. So effectively the excess hydroniums will be neutralized by the conjugate base. So therefore, to create this buffer, it's best to choose one where the minus log of the acid dissociation constant, or pKa, is close to the desired pH. So effectively having equal concentrations of the conjugate base and the acid in the solution makes the buffer more flexible for neutralizing both acids and bases. And the same logic applies if you have a buffer created from a weak base and conjugate acid. And generally you can't create a buffer from a strong acid and its conjugate base. So for example, hydrochloric acid, because the conjugate base, being the chlorine anion, is too weak to accept any protons to neutralize them. And we can apply the same logic to why we can't create a buffer from a strong base and its conjugate acid.